Okay, let's unpack this. Welcome to the deep dive.
Glad to be here.
Today, we're diving into backpropagation. It's really the core algorithm, isn't it? The thing that lets neural networks actually learn.
Absolutely. It's fundamental. You hear the term all the time, but getting a real feel for what's happening, well, that can be a bit tricky.
Exactly. And the source material we're looking at for this deep dive, some YouTube transcript excerpts, they give a really nice intuitive angle on it, which I appreciate. Skip some of the heavy math.
Right. So our goal here is pretty clear. Cut through that complexity, get to the heart of what backpropagation is actually doing, step by step.
Yeah, why it matters for training these networks. And we'll use those source excerpts as our guide.
Sounds good.
All right, so the source kind of assumes you, our listener, aren't coming in totally cold.
Yeah.
You've got a sense of what a neural network is, right? Layers of neurons, all connected up.
Yeah, the classic example being like recognizing handwritten digits. You might have, what, 784 inputs for the image pixels?
Mm-hmm.
Then maybe a couple of hidden layers, say 16 neurons each, and finally 10 output neurons, one for each digit, 0 through 9.
And you're also probably familiar with the basic idea of gradient descent. That's the whole optimization thing, finding the network's weights and biases that make the error as small as possible.
Finding the bottom of that error valley, so to speak.
Exactly. And that error, it's measured using a cost function. The source explains it pretty straightforwardly. For just one training example, like seeing an image of a 2,
Uh-huh.
the network spits out some values, maybe probabilities, for each output neuron. You compare that to what you wanted.
Which is ideally a 1 for the 2 neuron and else everywhere else.
Right. And the cost for that single 2 image is basically how far off the network was. Often it's like the sum of the squared differences between the actual output and the target output for all 10 digits.
And the total cost, the thing we really want to minimize, is just the average of that cost calculated over every single training example you have.
Tens of thousands, potentially.
Easily. So you average the error across all of them?
Okay, so gradient descent needs to find the negative gradient of that big total cost function, this gradient. It's like a giant arrow, isn't it?
Yeah, it's a vector pointing in the direction of steepest descent on the cost surface. It tells you precisely how to nudge every single weight and bias.
All at once.
All at once, yeah, to reduce that total cost most efficiently.
And this is where it gets kind of mind-bending, according to the source. For our little digit recognizer network,
Uh-huh.
that gradient vector could live in something like 13,000 dimensions. One dimension for every weight and bias.
Right. The source calls that beyond the scope of our imaginations, and calculating that huge, complicated gradient accurately, that's the real challenge.
Which is exactly what backpropagation is for. It's the algorithm that computes this crazy high-dimensional gradient.
Yep. That's its job.
But just thinking about a 13,000 dimensional vector, it doesn't give much intuition. Is there a better way to think about what the gradient means?
The source suggests a really helpful shift in perspective. Don't just think giant vector. Think, sensitivity.
Sensitivity. How so?
Well, each number, each component in that massive gradient vector corresponds to one specific weight or bias in the network.
Okay.
The size, the magnitude of that number tells you how much the total cost function changes if you wiggle that specific weight or bias just a tiny bit. It's how sensitive the error is to that parameter.
Oh, okay. So if one component of the gradient is big and another one is tiny.
It means the cost function is way more sensitive to changes in the first weight or bias. The source gives an example, like if the negative gradient component for one weight is 3.2 and for another it's 0.1, the cost is effectively 32 times more sensitive to the first weight. Changing that first weight will have a much bigger impact on reducing the error than changing the second one by the same amount.
I get it. So gradient descent isn't just moving randomly. It's using this sensitivity information to prioritize. It focuses the adjustments where they'll have the biggest effect, the most.
Bang for your buck, exactly, in
Yeah.
reducing the cost.
Right. So backpropagation is the engine that generates this map of sensitivities, these gradient components, for everything in the network.
Precisely. It tells gradient descent where the most effective changes are.
Okay, so let's get into how it does that. The source walks through the intuition by zooming in on just one training example first.
Right, let's stick with that image of a 2. Forget the thousands of others for a moment. For just this one image, how should it kind of nudge the network's weights and biases to lower its own contribution to the error?
And the process starts at the end, right? At the output layer.
Exactly. So the 2 goes in, the network does its thing, and maybe the outputs are, like we said, 0.5 for 0 minor, 0.8 for 1, 0.2 for 2, and so on. Random-ish, maybe.
But we wanted that 2 neuron to be close to 1 and the others near 0.
So the first step is to figure out the desired change for each of those output neuron activations. How much do we wish each one would go up or down?
And that desired change, that nudge, is proportional to the error.
It is. It's proportional to how far the current activation is from its target. So the 2 neuron, currently way down at point 2, needs a big positive nudge towards 1.
While maybe the 8 neuron is already at point 1, pretty close to its target of 0, so it needs only a small nudge, maybe slightly negative.
Exactly. The source points out that getting the 2 neurons activation up is sort of more important for fixing the error on this specific example.
Makes sense. Now, we can't just magically change those activations. How do we influence them?
The only things we can directly change are the weights and biases connecting into those output neurons from the layer before them, the last hidden layer.
Right. So let's focus just on that 2 neuron output neuron we want to boost. Its current activation, that point 2 value, came from a weighted sum of activations from the previous layer.
Plus its own bias term.
And then squeezed through some activation function,
Yeah.
like a sigmoid or real U, right? That nonlinear squishing function.
Correct. So if we want to increase that neuron's output, we have a few levers according to the source. We could increase its bias.
But giving it a head start.
Kinda, yeah. Or we could increase the weights on the connections coming into it. Or somehow we could influence the activations in that previous layer to be different.
Okay, let's talk about adjusting the weights first. The ones connecting from the previous layer to this 2 output neuron. How does Backprop decide which ones to tweak?
Well, think about the neurons in that previous layer. Some of them were probably more active, brighter, when the network saw this 2 image.
Okay.
The weights connecting from those already bright neurons have a bigger impact on our 2 output neuron. So if we want to boost the 2 output, increasing the weights from those highly active previous layer neurons gives us the most leverage. That's the best bang for your buck for this specific output neuron and this specific image.
I see. You strengthen the connections from the parts of the network that were already signaling maybe this is a 2 towards the actual 2 output neuron.
Yeah, exactly. The source makes a loose connection here to Hebbian learning neurons that fire together wire together. If a neuron in the previous layer is active when seeing a 2, strengthen its connection to the neuron that should be active for a 2.
But it's just a loose analogy the source is careful to say.
Right. It's more mathematically precise than just that phrase, but the intuition is similar.
Okay, so that's weights and the bias for the output neuron. What about the activations in the layer before it? We can't directly change them, but Backprop thinks about them.
It calculates what changes would be desirable in those previous layer activations to help the output neuron reach its target.
For our 2 output neuron that we want to increase, any previous layer neuron connected to it via positive weight, we'd ideally want that previous neuron to become even more active, brighter, and if it's connected by a negative weight,
Then we'd want that previous neuron to become less active, dimmer, to help our 2 neuron increase.
exactly. And the size of these desired nudges for the previous layer's activations is scaled.
Scaled by what? Proportional to the weight connecting it to the output neuron, and also proportional to how much that output neuron needed to change in the first place. Stronger connections and bigger output errors lead to bigger desired changes propagating back.
Okay. So for our single 2 image, we figured out how it wants to nudge the weights and bias feeding the output layer, A and D, what changes it wishes would happen in the activations of the layer right before that. But this feels like where the propagation part really kicks in.
Yes, this is the core idea, because everything we just discussed was just based on what the 2 output neuron wanted.
Right.
But remember, all the other output neurons, 0, 1, 3, 3, etc., also received inputs, produced an output, had an error, and therefore also have opinions, desired nudges about what should happen to those same neurons in the previous hidden layer.
Okay. So the 0 neuron wants certain changes in the previous layer to make its activation go down. The 1 neuron wants different changes, and so on.
Exactly. Backpropagation's cleverness lies in how it combines all these conflicting desires. For each neuron in that previous hidden layer, it sums up the desired activation nudges coming back from all the output neurons it's connected to.
Weighted by the connection strengths and the errors of those output neurons.
Precisely. This aggregated sum gives you the total desired change for each neuron's activation in that hidden layer, considering the needs of the entire output layer for this one example. That's the backpropagated signal.
And once you have that list of desired activation changes for the hidden layer, You just repeat the process.
You got it. It's recursive. Now you know how you wish the hidden layer activations had been different, so you apply the same logic. How should the weights and biases connecting into this hidden layer from the layer before it be changed to achieve these newly calculated desired activation changes?
When you keep stepping back, layer by layer.
Layer by layer, all the way back to the input. Calculating desired activation changes, and then using those to calculate the required changes for the weights and biases feeding into that layer.
What?
That's backpropagation for a single example.
Wow. Okay, so that gives us a set of nudges for every weight and bias, all based on just one input image, like R2.
But, as the source rightly points out, there's a big catch.
It's you only listen to the two.
Yeah. If you updated your network based only on what the two image wanted, the network would very quickly just start guessing 2 for everything. It wouldn't generalize.
Right, because the overall goal is to minimize the total cost across all the examples, not just one. So how do we get from the single example backprop to the gradient of the total cost?
Well, the conceptually pure way to do true gradient descent is kind of brutal. You run that whole backpropagation routine we just described for every single training example.
All tens of thousands of them.
Every single one. Each one calculates its own set of desired nudges for all the weights and biases.
And then what? You average them.
Exactly. For any given weight or bias in the network, you take the nudge calculated from the 2 image, the nudge from the 7 image, the nudge from the 0 image, all of them, and you average those nudges together.
And that collection of average nudges, one average nudge for every single weight and bias, that is essentially the negative gradient of the total cost function.
Loosely speaking, yes. That average tells you the best direction to update all parameters simultaneously to decrease the overall cost, considering the influence of all the training data.
Okay, but running backprop tens of thousands of times just to calculate the direction for one single update step. That sounds incredibly slow.
It is. The source calls it extremely long. Computationally, it's often just not feasible for large data sets and networks, which leads us to the practical approach.
Stochastic gradient descent, SGD.
SGD, exactly. This is how pretty much all large-scale deep learning training happens in practice.
How does it work differently?
Instead of using all the data for each step, you first randomly shuffle your entire training data set. Then you chop it up into smaller chunks called mini batches.
So maybe 100 examples per mini batch instead of 50,000.
Something like that, yeah. Could be 32, 64, 128, 100. Depends. And then, for each update step, you only run backpropagation on the examples within one mini batch.
Just those 100 examples.
Yep. You calculate the desired nudges just from those 100, average those nudges together, and then you update the network's weights and biases based on that mini batch average. Then you grab the next mini batch and repeat.
Ah, so the gradient you calculate from just one mini batch, it's not the true gradient of the total cost function anymore, is it? It's only based on a small sample.
Exactly right. It's an estimate or an approximation of the true gradient. It won't necessarily point in the absolute best direction downhill on the overall cost surface.
So the path downhill might be a bit more wobbly.
That's a great way to put it. The source has a fantastic analogy for this. It says, using mini batches makes the learning path a little more like a drunk man stumbling aimlessly down a hill but taking quick steps, rather than a carefully calculating man determining the exact downhill direction before taking a very slow and careful step.
That paints a perfect picture. You lose some precision in the direction of each step, but you get to take steps much, much more frequently.
Massively faster. The computational speedup is enormous.
And even though the steps are noisy and approximate.
By taking many of these fast, noisy steps, processing mini batch after mini batch, the network still generally heads downhill and converges towards a good solution, a local minimum of the cost function. It still learns effectively and gets really good on the training data.
So this whole machinery backprop, calculating the sensitivities, SGD using mini batches to approximate the updates, it's powerful stuff.
Hugely powerful. But the source brings up a really crucial point, a prerequisite that underpins all of this, which is often overlooked when just talking about the algorithm.
Which is?
You need data. Lots and lots of training data.
Right. The handwritten digit example, MNIST, is classic because someone went to the trouble of collecting and labeling thousands upon thousands of examples.
Exactly. The source mentions MNIST having so many examples that have been labeled by humans. Backpropagation can figure out the patterns, but only if you feed it enough labeled examples to learn from.
And that points to a major bottleneck in real-world machine learning, doesn't it?
Absolutely. Designing the network architecture, implementing backprop and SGD, that's often the easier part these days with modern libraries. The really hard, expensive, time-consuming part is often just getting enough high-quality labeled training data in the first place.
Having humans sit there and label images or transcribe audio or categorize text tens, hundreds of thousands of times.
That's frequently the real heavy lifting.
Okay, so wrapping up this deep dive on backpropagation, we've seen it's this clever algorithm that works backward from the output error.
Uh-huh. Calculating how sensitive the error is to every single weight and bias by propagating these error signals or desired changes layer by layer.
And then by averaging these signals, ideally over all data or practically using mini batches in SGD, we get the direction for gradient descent to adjust the network and make it learn.
We've stuck to the intuition, much like the source did. But yeah, the actual implementation involves calculus, chain rule, all that, but it builds directly on these core ideas of propagating errors backward.
And a huge takeaway, maybe the practical takeaway, is how utterly dependent this whole powerful learning process is on having access to large amounts of labeled data.
Definitely stands out. The algorithm is elegant, but it needs that fuel.
So reflecting on this, you have this sophisticated mechanism for self-correction, error signals flowing back, adjusting connections. It feels almost organic,
Mm-hmm.
but it's entirely reliant on this massive human-curated data set to get started.
It really makes you think, doesn't it? When we talk about building truly intelligent systems and we see how much effort goes into just labeling the data to train current approaches, what does that tell us about the real bottleneck? Is it still the learning algorithms themselves, or is it fundamentally about our ability to provide the right kind of experience, the right kind of data for these systems to learn from?